Hey, let's talk about half-life and radioactive decay. Here you see a fully worked out problem, step by step, and we will do a problem like this together, but first let's start out by identifying the equations, deriving some of these relationships, and understanding the concepts at play. So let's start by defining a new quantity that we're going to call the half-life. Half-life has the symbol T with a subscript of 1/2, and it represents the time it takes for, no surprise here, half of the nuclei of a radioactive substance to decay. So one way to think about this is by looking at an example. Let's say we have a sample of 8.32 times 10 to the 16th radioactive nuclei, and let's come up with a nice, neat half-life of 2 days. So we can complete a table showing the decay of these nuclei over time. So very easily we could say, okay, let's look at the number of days, and then let's look at the number of nuclei. So let's say on day 0 we start with 8.32 times 10 to the 16th, and if the half-life is 2 days, then 2 days later we're going to have exactly half of those nuclei, so 4.16 times 10 to the 16th nuclei, and then another 2 days later we're going to have half of that, so that's going to be 2.08 times 10 to the 16th, and so on and so forth. So after 6 days we're going to have half of that, which is 1.04 times 10 to the 16th. And if you were to graph this relationship, you'd be looking at a graph of exponential decay, which looks like this. So if this is the number of nuclei over time on the horizontal axis, we expect to see, no surprise here, a nice exponential decay function. Now the reason that we need an exponential decay function here is that we chose very nice and neat time values here. But what if we wanted to know how many nuclei were present after 10.5 days, or some multiple of 2 here, number of days? Then we would need a function to calculate how many particles are remaining after that amount of time. So what we need to do is develop a function that's going to look at the number of nuclei after an arbitrary time t. So to do that, we're going to use an exponential decay function. And the function that we're going to use is n, which is the number of nuclei, is going to equal n naught, which is the initial number of nuclei, times e, Euler's number, raised to the negative lambda t. So let's unpack this equation step by step. N, as we said, is equal to the number of nuclei. N naught is equal to the initial number of nuclei. Lambda is a new quantity for us, and this is known as the decay constant. And we're going to derive in a moment a way to calculate the decay constant once you know the half-life. So let's also indicate that t is simply the time elapsed. All right, so you can see from this function that as time increases, because there's a negative exponent on this e here, as time goes up, this function is going to decrease. So this is consistent with what we expect from exponential decay. As time goes up, the number of nuclei will go down. So let's go ahead and let's express the decay constant lambda. We're going to say that the decay constant lambda can be expressed in terms of the half-life. So right now we're going to run through the derivation for how you can relate the decay constant lambda to the half-life t 1/2. All right, so let's do that together. We're going to start out by assuming that we lose exactly half of our nuclei, right? So if we start out with the equation n equals n naught e to the negative lambda t, If we lose half of our nuclei, then the new number of particles will be exactly 1/2 of the initial n naught. And that's going to equal n naught e to the negative lambda t. Now, obviously, the n naughts here will cancel, and so now we're left with 1/2 equals e to the negative lambda t. If we want to solve for, let's say, this lambda, let's consider that we have defined this amount of time to be the half-life, right? If we lose half of our particles, that means we can replace this t with the half-life t 1/2. So let's rewrite this equation with t 1/2 in here. So now we have 1/2 equals e to the negative lambda t 1/2. Okay? So now what we're going to do is we're going to unpack this and solve for lambda. Now, to get lambda by itself, we have to get it out of the exponent. To get it out of the exponent, we have to take the natural logarithm of both sides. Because how do you undo the exponential function? You have to use the natural logarithm. Okay? So we're going to take the natural logarithm of both sides. And if you take the natural logarithm of e to the negative lambda t 1/2, the natural logarithm is the inverse function of the exponential function, and so this will simplify exactly to negative lambda t 1/2, and now over on the left side we have the natural logarithm of 1/2. Okay, so now to get lambda by itself, we could divide both sides by negative t 1/2 divided by negative t 1/2, and so now we're able to express our lambda as the natural logarithm of 1/2 divided by negative t 1/2. Now this is kind of an awkward expression. What we want to do is take advantage of one of the properties of logarithms to express the logarithm of a fraction. You can express the logarithm of this fraction using the property that the logarithm of a fraction can be written as the logarithm of the numerator, so the logarithm of 1, minus the logarithm of the denominator, the logarithm of 2, all divided by negative t 1/2. And let's not forget that there's still a negative, but it's in the denominator for now, and that's fine. Okay. Now let me ask you a question. What's the natural logarithm of 1? In other words, what's the power of e that gives you 1? Well, the power of anything that gives you 1 is always 0. Anything raised to the 0 is 1. So the natural logarithm of 1 is precisely 0. So that can be written as negative logarithm of 2 divided by negative t to the 1/2, or rather t 1/2, half-life, or the negatives cancel, natural log of 2 over t 1/2. And that leads us to our final equation that we need to use here, which is lambda, the decay constant, can be written as the natural log of 2 divided by the half-life t 1/2. Okay, let's take a moment. Let's put this equation into a rectangle. Let's star this, and let's smiley face it, because this equation is a big deal. This equation will allow us to take the half-life and convert it into a decay constant. Alright, so now that we have an equation for our decay constant, let's go ahead and consider an example. Alright, so our example looks like this. The half-life of the carbon-14 nucleus is 5,730 years. A sample originally containing 4.35 times 10 to the 17th nuclei decays to 6.22 times 10 to the 12th nuclei. And the question is, how old is the sample? So what we need to do here is look at how do we calculate time? Where is time here? Well, you can see time in the exponential decay function n equals n naught e to the negative lambda t. So we really want to solve for this t. So what do we have at our disposal? Well, we have the final number of atoms. So this is 6.22 times 10 to the 12th, and that's going to equal the initial number of atoms, 4.35 times 10 to the 17th. Okay, that's going to be equal to, or times e to the negative lambda t. So presumably, if we can figure out what lambda is, we can plug that in and then solve for t. Now, one thing that we might do at this stage, just to kind of clean this up a little bit, is divide both sides by 4.35 times 10 to the 17th. And if I'm not mistaken, that's going to yield for us 1.43 times 10 to the negative 5th. All right. And we're going to say, all right, that's got to be equal to this e to the negative lambda t. Okay, so let's hold on to this for a second, and let's take a moment to calculate lambda. Lambda can be found, as we just derived, lambda can be found as lambda equals the natural log of 2 divided by the half-life. So we can say lambda now is going to be the natural log of 2 divided by the half-life of 5,730 years. 5,730 years. So this is going to provide us with a decay constant of 1.21 times 10 to the negative 4th with a unit of years to the negative 1. In other words, 1 over years, because there's a years in the denominator of this equation. All right, so there's our lambda, 1.21 times 10 to the negative 4th, years over 1, or 1 over years. All right, very nice. So now, let's go to where we have a little bit more space, and let's finish this problem. So we're going to say, all right, we left off with 1.43 times 10 to the negative 5th equals e to the negative, and now we're going to put in our lambda. Our lambda is 1.21 times 10 to the negative 4th. Now it's all SI units here, so I'm not going to worry about the units, times t. Now the question is, how do we unpack this equation and get t? Well, just like we did earlier, the way that you get the t out of the numerator is by undoing the exponential function. How do you undo the exponential function? You have to take the natural logarithm. So we're going to take the natural log of both sides, so natural log of 1.43 times 10 to the negative 5th, and that's going to equal, again, the natural log will cancel out the exponential function, and you're going to be left with negative 1.21 times 10 to the negative 4th t. All right, so now this is something we can just put into our calculator, and if you take the natural log of this number, you will get negative 11.16. And that's going to equal negative 1.21 times 10 to the negative 4th times t. So all that's left is to divide both sides by negative 1.21 times 10 to the negative 4th. And we are left with a t. Notice that the negatives cancel, which is important because you want time to be positive here. The t will be 92,200 with a unit of years. So that sample is 92,200 years old. Well, I hope that was helpful, and thanks for watching.